Hello, my dear friends. Tonight we leave the quiet stone corridors of monasteries and travel much further back in time to a world of noise, movement, and enormous cities. Imagine you are standing at sunrise on a hill above the city of Rome, nearly 2,000 years ago. Below you spreads a city far larger than any medieval town, a place filled with stone buildings, smoke rising from bakeries, voices echoing across streets, and carts already rolling over paved roads. People walk quickly because the day begins early. Water flows through fountains. Vendors prepare stalls. Soldiers march toward the gates. And all around you, almost unnoticed by the people living inside it, a vast network of technology quietly keeps the city alive. The Romans themselves did not use the word technology as we do today. They simply called it engineering, craft, or practical knowledge. Yet what they built was so organized and so reliable that many parts of their system continued to be used for more than 1,000 years after their empire faded. Their achievement was not one single invention. It was the careful combination of many ideas working together at the same time. The first thing a traveler to Rome would notice was water. In most ancient cities, water came from wells or nearby rivers and had to be carried by hand. But Rome held hundreds of thousands of people, far too many for buckets alone. Instead, high above the city, long lines of stone arches stretched across the countryside. These were aqueducts, channels designed to carry fresh water from distant hills into the city without pumps or machines. The Romans relied on gravity. Engineers surveyed land carefully, measuring slopes so the water would flow gently downhill for miles. The decline was so slight that in some places the water dropped only a few meters over many kilometers. Yet the flow never stopped. Inside the aqueduct ran a covered channel lined with waterproof cement. The water moved slowly and steadily, protected from sunlight and contamination. At the edge of the city, it entered distribution tanks, and from there, it divided into many directions. Some water went to public fountains where ordinary citizens filled jars. Some supplied public baths. Some went to wealthy houses, and a portion was reserved for cleaning streets and flushing sewers. This was not a simple pipe. It was a managed network. Because water flowed constantly, Rome could support daily bathing. Public baths were not rare luxuries, they were ordinary parts of life. Large bath complexes contained warm rooms, hot rooms, and cold pools. Heating these spaces required another Roman innovation: underfloor heating. Beneath the stone floors, workers built small pillars supporting a raised surface. Hot air from furnaces moved through the empty space below and then through hollow walls, warming entire rooms evenly. A visitor entering the baths felt gentle heat rising from the floor itself. This system, called the hypocaust, was one of the earliest forms of central heating. All of this required materials capable of lasting for centuries. Here the Romans used a discovery that may be their most important: concrete. Earlier cultures built mainly with cut stone blocks. The Romans learned to mix volcanic ash with lime and water, creating a material that hardened even underwater. They poured this mixture into wooden molds and created walls, domes, and harbors far stronger than ordinary stone construction. Because concrete could be shaped, architects designed curved ceilings and vast interior spaces. The great domes of Roman buildings stood not because of decoration, but because of chemistry and careful mixture ratios. Roads formed another part of the system. Roman roads were not simple dirt paths. Workers dug deep foundations, filled them with layers of gravel and sand, and placed fitted stone slabs on top. The surface was slightly curved, so rainwater ran off into side ditches. These roads remained firm in wet weather and allowed wheeled vehicles to travel long distances. Milestones marked distances, and official stations offered fresh horses for messengers. Messages could cross hundreds of kilometers in a matter of days, connecting the empire administratively. The roads, aqueducts, baths, and heating systems were not separate achievements. They depended on each other. Roads allowed materials to reach cities. Aqueducts supplied baths and fountains. Concrete enabled arches to carry water over valleys. Heating systems made bathhouses comfortable year-round. Each part supported daily urban life, and because maintenance crews constantly inspected them, the system kept functioning. Even waste was managed. Beneath the streets of Rome ran large drainage tunnels. Rainwater and wastewater flowed through these channels toward the river. Public latrines connected to the same system, flushed by running water from the aqueduct supply. The arrangement reduced standing waste in crowded areas and made dense population possible. Without such planning, the city could not have grown so large. As evening approached in Rome, lamps were lit along streets, shops closed gradually, and the fountains still flowed as they had all day. Most residents did not think about the arches beyond the hills or the channels beneath their feet. The technology worked quietly, almost invisibly. The Romans did not admire it as a marvel. They depended on it as routine. And as we continue, we will move from water and cities into the tools, machines, and measuring devices that allowed Roman engineers to build with such precision, exploring how they surveyed land, lifted heavy stone, and organized construction on a scale that would not be matched again in Europe for many centuries. Now that the water flows into the city and the streets are alive, we move closer to the builders themselves, because the true strength of Roman technology did not begin with buildings. It began with measurement. Before a single stone was placed, Roman engineers spent long hours simply observing land. They stood quietly in open fields with instruments that looked simple but required great patience to use. One of these tools was called the groma. It consisted of a vertical pole with horizontal arms and hanging cords. By aligning the cords carefully with distant markers, surveyors could create perfectly straight lines across uneven terrain. With this method, they laid out roads, city streets, and even military camps so precise that many still match modern maps. Another device, the chorobates, was used to measure level ground. It was essentially a long wooden bench with a shallow water channel carved along the top. When water rested evenly inside the channel, the engineer knew the surface was level. Using this method, they could maintain the gentle slope required for aqueducts. The slope had to be exact. If the angle became too steep, water would rush and damage the channel. If it became too flat, the flow would stop. Because they lacked modern machines, their accuracy depended entirely on careful observation and repetition. Teams walked mile after mile, marking the correct path long before construction started. Once measurement was complete, construction began with organization. Roman building projects were not chaotic gatherings of workers. They were planned operations. Each group had a specific task. Stonecutters shaped blocks, laborers carried materials, carpenters built scaffolding, and skilled engineers supervised alignment. The Roman army itself often acted as a construction force. Soldiers were trained not only to fight but also to dig trenches, erect bridges, and assemble fortifications. Military discipline made large projects possible because thousands of workers could follow coordinated instructions. Lifting heavy materials required machines. The Romans developed cranes powered by human or animal strength. A typical crane included a tall wooden frame and a wheel large enough for a man to walk inside, much like a giant hamster wheel. As the worker walked, the rope wound around a drum and lifted stones upward. Using pulleys multiplied force, allowing relatively small teams to raise massive blocks onto walls or arches. These machines appeared in harbor construction, temples, and amphitheaters. Without them, many of Rome's famous structures could never have been completed. Bridges reveal the same careful thinking. Roman engineers preferred arches rather than flat beams. An arch transfers weight sideways into its supports rather than downward alone. By placing wedge-shaped stones called voussoirs around a central keystone, they created structures capable of holding great loads. Once the final stone was set, the entire structure locked together. Even after the wooden support frame was removed, the bridge remained stable. Many of these bridges still stand because the design distributes pressure naturally into the ground. Concrete again played a role here. Instead of cutting enormous stones for every wall, builders poured concrete between brick or stone facings. The outer layer gave shape and strength, while the interior hardened into a solid mass. This allowed faster construction and stronger foundations. Harbor engineers even poured concrete underwater using wooden boxes to contain the mixture until it hardened. Entire breakwaters and docks were created this way, enabling ships to anchor safely and ensuring steady trade. Roman ports depended on mechanical devices as well. Warehouses used hoists and ramps to move cargo. Grain arriving from distant provinces had to be unloaded quickly before spoilage. Engineers designed storage buildings raised above ground to allow air circulation and reduce moisture. In large cities like Rome, feeding the population required coordination as complex as the aqueducts supplying water. Time itself was measured technologically. Public spaces often displayed sundials calibrated for the city's latitude. Some wealthy homes used water clocks in which water dripped slowly from one container to another, marking passing hours. This allowed officials to schedule courts, markets, and public events with consistency. While modern clocks did not exist, daily activities followed reliable timing thanks to these systems. Communication across distance also relied on planning. Along major roads stood signal towers and relay stations. Mounted messengers carried official orders, changing horses at intervals. Because roads were straight and carefully maintained, travel remained predictable. Administrative control over a vast empire depended as much on road engineering as on military strength. We should also notice the attention given to maintenance. Aqueduct channels were inspected regularly. Sediment was removed so flow remained clear. Road surfaces were repaired where stones loosened. Public buildings employed caretakers responsible for cleaning and upkeep. The Romans understood that technology was not simply invention, it was continuous care. A system lasted only if people watched over it. In the quiet of evening, after construction sites emptied and tools rested, the results remained visible. Straight roads stretching into distance, bridges crossing rivers, and buildings standing solidly against time. The workers themselves rarely left written praise of their achievements. yet their methods were recorded in manuals used by later generations. The knowledge did not disappear quickly. For centuries after Rome declined, travelers encountered roads and aqueducts still functioning. And as we continue further, we will enter the heart of Roman cities themselves, exploring how apartments, shops, heating systems, and even glass windows changed daily life for ordinary citizens who lived surrounded by this network of engineering. Now we step away from the builders and into the homes of ordinary people. Because Roman technology was not only for grand monuments or imperial palaces. It shaped daily living for citizens, merchants, and workers who never met an emperor, yet relied constantly on engineering around them. To understand this, imagine yourself entering a busy Roman neighborhood inside the city walls. Tall apartment buildings rise several floors high along narrow streets. These are called insulae, and they house many families in a small space. The ground floor contains shops, bakeries, taverns, cloth sellers, while upper levels hold living rooms and sleeping spaces. Without certain technologies, such crowded living would have been impossible. Water fountains nearby provided fresh supply throughout the day. Residents carried jars up staircases, but the steady flow meant they did not depend on a single well. Public fountains were placed deliberately so no district was too far from running water. The streets themselves were engineered for drainage. They were slightly raised in the center so rainwater moved towards side gutters. Flat stepping stones crossed at intervals, allowing pedestrians to pass without stepping into mud while carts rolled between the stones. Even after heavy rain, movement could continue. This may seem simple, yet it allowed a dense city to function through all seasons. Inside wealthier houses, technology became even more visible. Roman homes were arranged around open courtyards called atriums. At the center sat a shallow basin that collected rainwater from the roof opening above. This water flowed into underground storage tanks, providing additional supply for washing and cleaning. In many homes, pipes made from lead or terracotta distributed water into different rooms. Small fountains decorated gardens, their constant sound part of daily life. Heating again appears here. The Hippocaust system, which warmed bathhouses, also heated private villas. Beneath floors ran hollow spaces connected to furnaces tended by workers. Warm air circulated below and inside the walls, turning cold winter nights into comfortable evenings. In northern provinces where winters were harsher, this innovation made Roman settlements far more livable than earlier dwellings. Lighting was another everyday technology. When evening came, families lit oil lamps made of clay or bronze. Olive oil fueled a small wick, producing steady light without excessive smoke. Shops remained open later because of this reliable illumination. Workshops could continue tasks into early night hours. The ability to extend the day even slightly changed productivity across the city. Glass production also advanced daily comfort. Early windows elsewhere were covered with cloth or shutters, but Roman glassmakers learned to create thin, translucent panes. Though not perfectly clear, they allowed light inside while blocking wind and rain. Rooms became brighter and warmer. Greenhouses even appeared in some estates where plants were grown under glass protection during cooler months. Food preparation depended on engineered tools as well. Bakeries used large stone mills turned by animals to grind grain into flour. Ovens built from brick retained heat long after firewood burned down, baking bread evenly. In crowded cities, many residents bought bread from professional bakers rather than baking individually. This system required coordination of grain supply, milling, baking, and sale, all supported by roads and storage warehouses. Public baths again played a major role in daily routine. Citizens visited not only for washing but for social life. Heated rooms, warm pools, and cold baths followed a sequence designed to relax muscles and clean skin. Water flowed constantly through the complex, entering fresh and leaving through drainage channels. Workers maintained furnaces, scrubbed floors, and monitored water temperature. The bathhouse became a center of urban life made possible entirely by engineering. Even entertainment relied on technology. Amphitheaters and theaters were constructed with careful acoustics so voices carried without amplification. Stone seating rose in curved patterns designed to reflect sound toward the audience. Thousands could hear a speaker or performer clearly because architects understood how shape affected sound waves, even if they did not describe it scientifically. Waste disposal, often overlooked, was essential. Public latrines used flowing water beneath seats to carry waste into sewers. Sponges attached to sticks were rinsed in running channels for cleaning. While not modern sanitation, it represented organized urban management far beyond simple pits or open streets. In dense populations, such planning reduced disease and made city life more sustainable. As night deepened, families gathered around small lamps, hearing distant sounds of carts over stone roads and water splashing in fountains. They might never think about aqueduct slopes, surveying tools, or cranes lifting stone. Yet every comfort around them depended on those systems. The Roman achievement was not a single invention admired once. It was a network supporting ordinary life every day, and as we continue, we will leave the city streets and travel outward across the empire, seeing how the same technologies allowed Roman armies to move, camps to be built overnight, and distant provinces to feel connected to a capital many hundreds of miles away. Now we leave the crowded streets of the city and walk outward along one of those straight Roman roads, because beyond the comfort of urban life stood another reason Roman technology became so famous: the army. Roman military strength was not only discipline or numbers, it depended heavily on engineering. A Roman army did not travel like a wandering group of soldiers. It moved like a carefully organized construction force capable of building a small city almost every single night. As a marching column advanced across the countryside, surveyors walked ahead carrying measuring tools. Before the soldiers even stopped, the ground was already being chosen for a camp. They looked for gentle slopes, nearby water, and open visibility. Once the site was marked, the soldiers themselves began construction. Every man carried tools alongside his weapons: shovel, pickaxe, wooden stakes, and basket. Within hours, a defensive trench was dug around a large rectangle. The earth removed from the trench formed a raised bank, and on top of it they placed sharpened stakes to create a protective wall. Inside the camp, streets were laid out in straight lines crossing at right angles. The command tent always stood at the center, with barracks tents arranged in orderly rows around it. Even temporary camps followed nearly identical patterns no matter where the army traveled. Because of this standard design, soldiers always knew where to find supplies, officers, and exits without confusion. The camp itself was technology, not a building, but a repeatable system allowing thousands of people to live safely in hostile territory. Road construction followed the army. When a region became part of the empire, engineers improved routes so carts and troops could move quickly. Workers first cleared vegetation, then dug deep trenches and filled them with layers of stone and gravel. The final surface used fitted paving stones placed tightly together. These roads did not easily turn to mud during rain. They allowed wagons carrying food, weapons, and messages to travel steadily in all seasons. Some routes extended for hundreds of kilometers, linking distant provinces directly to Rome. Bridges accompanied these roads. Rather than detouring around rivers, Roman engineers crossed them. Wooden bridges could be built quickly for temporary use, but permanent crossings used stone arches anchored into riverbanks. Construction sometimes happened while water still flowed beneath, with temporary supports holding stones until the keystone locked them together. Travelers moving along the empire could cross rivers safely because of these reliable structures. Military logistics depended on storage technology as well. Grain warehouses called horea were built on raised floors supported by pillars. Air could circulate underneath, preventing moisture from spoiling food. Thick walls kept temperature stable. Armies marching far from farms needed predictable supply, and these buildings made long campaigns possible. The army also used signaling systems. Watchtowers stood along borders and roads. Fires or smoke during daylight carried messages across distances rapidly. A signal lit on one tower could be seen by the next, passing information faster than a messenger riding alone. Frontier defenses, especially along northern borders, used lines of forts connected by such communication. The result was not simply a wall, but a monitored boundary. Water engineering accompanied soldiers as well. Camps near rivers dug channels to bring water inside safely. In permanent forts, small aqueducts carried fresh water into baths and fountains, just like in cities. Even at remote frontiers, soldiers bathed regularly because engineers built heating systems and drainage similar to those at home. Roman military life relied on maintaining familiar routines, and technology allowed that consistency. Siege warfare demonstrated another side of Roman engineering. When facing fortified towns, the army did not rely only on direct assault. Engineers constructed ramps of earth and wood to reach walls. Towers on wheels allowed archers to fire from equal height. Large throwing machines powered by twisted ropes launched stones or bolts to weaken defenses. These devices required mathematical understanding of tension and angle, even if described practically rather than theoretically. Because camps, roads, bridges, and machines could be built repeatedly and reliably, the army remained supplied and coordinated. Victories often depended on movement and preparation more than sudden combat. A well-built road might determine the outcome of a campaign by allowing reinforcements to arrive sooner. When evening settled over a marching camp, fires glowed behind the defensive bank. Guards watched from the gate towers, and soldiers rested, knowing the same protective layout surrounded them as it had the night before. The system traveled with them. Wherever they stopped, Roman order appeared. And as we continue, we will turn toward another quieter achievement: how Roman engineers measured time, organized calendars, and coordinated daily schedules across an empire so vast that sunrise occurred hours apart between its eastern and western edges. As the army camps rest for the night and the roads stretch quietly into the distance, we now turn to something less visible, but just as important to Roman life: the organization of time itself. A vast empire cannot function only with roads and buildings. People must know when to meet, when courts open, when markets begin, and when taxes are due. The Romans approached time with the same practical thinking they applied to engineering. Before accurate mechanical clocks existed, the daily schedule depended on observation of the sun. Public squares often contained large stone sundials carefully aligned to the sky. A metal pointer cast a shadow across marked lines, and by watching its movement, citizens could estimate the hour. Officials announced the beginning of the workday and the closing of courts based on this measurement. Because the sun's path changes through the seasons, the Romans adjusted expectations. Summer days were divided into longer daylight hours, while winter days contained shorter ones. Their hours were therefore flexible, but they remained predictable enough for coordination. For indoor use and cloudy days, water clocks offered another solution. A container filled slowly or emptied at a steady rate through a small opening. Markings along the interior indicated passing intervals. Magistrates used these clocks in courts to limit the length of speeches. Speakers knew they had only as much time as the water allowed. This simple device created fairness in legal proceedings and ensured cases moved forward without endless delay. The Roman calendar also shows technical thinking. Earlier systems drifted away from the seasons, creating confusion for agriculture and festivals. In the 1st century BCE, a major reform introduced a fixed calendar based on the solar year. Months gained consistent lengths, and an extra day was added periodically to keep alignment with the seasons. This reform, known today as the Julian calendar, became the foundation for calendars used in much of the world for centuries afterward. Farmers could plant at expected times, and administrators could schedule taxes and contracts with reliability. Measurement extended beyond time to space. Land surveyors mapped fields for taxation using ropes and measuring rods. They divided land into rectangular plots that could be recorded on official tablets. Many modern property boundaries in parts of Europe still follow these ancient divisions. The careful mapping ensured fairness in taxation and clear ownership, reducing disputes between neighbors. The postal system also relied on this organization. Along major roads stood relay stations where messengers changed horses and rested briefly. Official correspondence moved steadily across provinces. Because distances were measured and routes maintained, administrators in Rome could receive news from far regions faster than one might expect in the ancient world. Orders traveled outward while reports returned inward, forming a continuous exchange. Even public entertainment required coordination. Amphitheater events were announced in advance. Markets opened at predictable hours. Religious festivals followed the calendar precisely, drawing crowds at known times each year. The rhythm of daily and seasonal life became synchronized across cities separated by great distances. Inside homes, people organized their day around these shared patterns. Morning business took place after sunrise announcements. Midday brought rest or bathing. Evening meals occurred before darkness deepened. Though no mechanical clock ticked on a wall, society moved with a regular pulse guided by observation, measurement, and shared understanding. What makes this remarkable is not the complexity of any single device, but the consistency across the empire. A merchant traveling from one province to another encountered familiar schedules and expectations. Courts opened at similar times, roads followed similar markers, and calendars matched. This predictability encouraged trade and communication because travelers knew what to expect upon arrival. Thus, Roman technology included not only physical structures but systems of coordination. By organizing time and measurement, they connected distant communities into a single functioning network. The empire's stability depended as much on shared schedules as on stone roads. And as we continue, We will explore how knowledge itself, books, maps, libraries, and teaching, allowed Roman technical ideas to be recorded and passed along, preserving their methods long after individual builders had finished their work. Now we move from roads and schedules to something quieter, but just as powerful: the preservation of knowledge. Roman technology did not exist only in the hands of builders. It also lived in writing. The Romans carefully recorded methods, instructions, and observations so that future engineers could repeat the same results even years later. In this way, their achievements became not just physical structures, but shared understanding. In cities across the empire stood libraries and archives. Some were grand public buildings. Others were simple rooms attached to administrative offices. Inside, wooden shelves held scrolls made from papyrus. Each scroll contained writing copied carefully by trained scribes. These were not only poems and histories. Many contained practical information, descriptions of construction, agriculture, medicine, and surveying. An engineer could read instructions written by someone he had never met and apply them in a different province far away. One of the most valuable texts described architecture and building techniques in careful detail. It explained proportions of buildings, placement of columns, mixing of materials, and even how to test soil before laying foundations. Instructions discussed ventilation, light, and comfort within rooms. This shows that Roman builders did not rely entirely on guesswork or tradition. They studied, recorded, and taught. Maps also played a major role. Surveyors drew diagrams showing roads, rivers, and distances between towns. Some maps were not accurate in modern geographic shape, but they displayed routes clearly, showing travelers how far they needed to go and where to find stops along the way. Military commanders used these maps to plan marches. Merchants used them to estimate travel time and supply needs. The empire became easier to navigate because knowledge was organized visually. Education supported this system. Young men training for administrative or engineering careers studied arithmetic and geometry. They learned to calculate areas of land, volumes of storage, and alignment of structures. Even if they lacked modern formulas, they understood proportions and measurement practically. Teachers demonstrated how triangles helped determine height of buildings or distance across rivers. With simple tools and careful reasoning, they solved real problems. Construction workshops acted as schools as well. Apprentices worked beside experienced craftsmen, learning how to cut stone, mix mortar, and assemble arches. Knowledge passed through observation and repetition. A young worker might begin by carrying materials, then progress to shaping bricks and eventually supervise smaller tasks. Over time, he understood not only how to build, but why certain methods worked better than others. Medical knowledge was recorded similarly. Doctors wrote about herbs, treatments, and surgical tools. While medicine was limited by modern standards, the practice of documenting experience allowed improvement over generations. Hospitals near military forts treated injured soldiers using organized care and recorded observations about recovery. Even agriculture benefited from written instruction. Manuals described planting seasons, irrigation methods, and soil preparation. Farmers could follow advice developed in other regions, increasing productivity. Because food supply supported cities and armies, agricultural efficiency formed another part of technological success. We should also notice the materials used for writing. Papyrus scrolls were common. but wax tablets served daily use. A wooden frame filled with wax allowed messages to be scratched into the surface with a stylus and then smoothed for reuse. Officials used these tablets for temporary notes, calculations, and correspondence. In a sense, they were early reusable notebooks, helping administrators track supplies and accounts. Communication between regions depended on this recorded knowledge. When an engineer traveled to a distant province to repair an aqueduct or build a bridge, he did not begin from nothing. He carried measurements, drawings, and instructions. Because methods were written down, Roman technology could be repeated reliably far from its origin. As the evening settles across the empire, scribes continue copying scrolls by lamplight, preserving information that might outlast the buildings themselves. Stone arches may crumble centuries later, but the written descriptions would guide future builders who discovered them. In this way, Roman technology lived not only in concrete and brick, but in memory and instruction. And as we continue further, we will explore how trade and manufacturing spread these ideas even more widely, allowing tools, materials, and inventions to travel across seas and deserts to reach the far edges of Roman territory. From written knowledge, we now move into movement. Not the movement of armies, but the steady flow of goods. Roman technology spread most effectively through trade. Roads and ports were not built only for soldiers or officials. They carried materials, tools, and ideas across enormous distances, connecting forests in the north, deserts in the south, and busy harbors around the Mediterranean Sea into one working system. Along the coasts stood large harbors protected by curved breakwaters made from concrete poured directly into the water. Ships could enter safely even when waves struck the shore outside. Inside the harbor, cranes stood beside docks, lifting cargo from ships to storage areas. Workers unloaded sacks of grain, jars of oil, glassware, metal tools, and cloth. Because unloading was organized and sheltered, trade continued in many weather conditions. Merchant ships themselves reflected careful design. They used wide hulls to carry heavy cargo and deep keels to stabilize movement across open water. Large square sails captured steady wind, allowing ships to cross long distances without constant rowing. Navigation relied on observation of stars, coastline landmarks, and experience passed from sailor to sailor. While simple compared to modern navigation, it proved reliable enough to maintain regular trade routes linking Egypt, North Africa, Greece, and Italy. One of the most important transported goods was grain. Cities the size of Rome could not grow enough food nearby. Ships brought wheat from distant provinces. Enormous storage warehouses near the harbor protected supplies from moisture and pests. Grain was then distributed gradually to bakeries, ensuring steady bread production. This system required coordination between farmers, sailors, dock workers, and millers. Without reliable transport technology, urban life would have collapsed quickly. Trade also spread materials used in construction. Stone quarries produced blocks cut to standard shapes so they could be fitted efficiently at building sites. Marble from one region appeared in temples hundreds of kilometers away. Timber from distant forests became roof beams in cities far from the source. Because roads allowed heavy wagons to travel, builders were no longer limited to local resources. Manufacturing centers developed where materials and transport met. Pottery workshops produced large quantities of identical containers, especially amphorae, tall clay jars with narrow necks and pointed bases. These jars carried olive oil, wine, and preserved foods. Their shapes were standardized so they could be stacked tightly in ship holds. Broken pieces of amphorae found across the Mediterranean today reveal the scale of distribution. Metalworking also advanced. Iron tools such as chisels, saws, and nails improved construction efficiency. Bronze fittings strengthened doors and machinery. Skilled smiths heated metal in furnaces and shaped it with hammers and molds. Because materials could be shipped widely, tools made in one region were used far away. This sharing of equipment helped unify building practices across the empire. Glass production spread similarly. Workshops learned to blow molten glass into containers and windows more quickly than earlier methods. Transparent vessels, lamps, and panes traveled along trade routes, appearing in homes and bathhouses. Light entering through glass transformed interiors and made enclosed spaces more comfortable. Coins formed another part of technological organization. Standardized currency allowed merchants to trade without constant barter. A coin minted in one city could be accepted in another because weight and metal content were regulated. This stability encouraged travel and exchange. Traders knew the value of goods across distances, simplifying transactions. Markets inside cities reflected the results of this network. A citizen in Rome might purchase oil pressed in Spain, spices from eastern lands, and glassware made in Syria, all in a single day. Such variety was possible only because transportation, storage, and production were coordinated through engineering and planning. As night falls over a harbor, ships rock gently at their moorings while warehouse guards watch over cargo. Far inland, roads carry wagons under starlight toward towns waiting for supplies. Technology here is not a machine, but a system. Ships, containers, coins, roads, and buildings working together to move resources where they are needed. And as we continue, we will look at how Roman engineers also turned their attention to leisure and comfort, creating theaters, arenas, and public spaces designed not only to function, but to entertain large crowds safely and efficiently. As trade moves quietly across seas and roads, we now return to the city itself, not to its homes or workshops, but to its gathering places. Roman engineers did not build only for survival and administration. They also designed spaces for crowds, thousands of people meeting together for performances, ceremonies, and public events. Creating comfort and safety for such large gatherings required careful planning, and here again technology appeared in forms people often took for granted. The Roman theater was one of the first examples of large-scale acoustic engineering. Instead of placing a stage in an open field, builders shaped the seating area into a half-circle rising upward in stone steps. This curved arrangement allowed sound to travel naturally. When an actor spoke at the front, his voice moved outward and upward, reflected by the shape of the seating rows. Even people sitting high above could hear clearly without shouting. Architects did not describe sound waves mathematically, but through observation they learned which shapes carried voices best, and repeated those shapes in many cities. Amphitheaters, built for larger spectacles, required even greater attention to structure. The most famous example is the Colosseum, but many smaller cities had similar buildings. From outside it appeared as stacked rows of arches forming a giant oval. These arches were not decoration. Each one supported weight from above and distributed pressure through the structure into the ground. Because arches shared the load, the building remained stable despite enormous size. Inside, engineers solved the problem of movement. Tens of thousands of spectators could enter or leave through multiple passageways called vomitoria. These corridors were arranged so that people spread naturally through different levels, rather than crowding a single gate. Wide staircases and numbered seating sections guided visitors to their places efficiently. Even without modern signage, the design itself directed movement. A large event could end, and the building empty surprisingly quickly. Shade and comfort were considered as well. Large amphitheaters used a system of ropes and fabric coverings called the velarium. Sailors, experienced in handling ropes, controlled these coverings from above. They stretched across the seating area, reducing direct sunlight during hot afternoons. Poles anchored around the top edge supported the fabric, and adjustments followed the sun's position. This was an early example of large movable roofing designed for public comfort. Water again played a role. Some arenas could be flooded temporarily for staged naval displays. Channels beneath the floor carried water in and out through controlled openings. Although used only on special occasions, the existence of such a system shows how flexible Roman engineering could be when spectacle demanded it. Public squares or forums also required planning. Paved surfaces allowed markets and assemblies even after rain. Covered walkways protected pedestrians from sun and weather. Drainage channels prevented standing water. Government buildings around the square followed symmetrical layouts so visitors could navigate easily. The forum became both administrative center and social meeting place supported by thoughtful design. Even seating reflected order. Stone benches were placed at consistent heights and depths to support the body comfortably for long periods. Steps doubled as seats, reducing the need for separate furniture. Small details such as handrails, guard walls, and evenly spaced entrances reduced accidents in crowded conditions. Lighting extended activity into evening hours. Torches and oil lamps mounted along corridors illuminated exits after sunset. Workers maintained these lights so spectators could leave safely. The aim was not only to impress but to manage crowds effectively. These public spaces demonstrate that Roman technology addressed human behavior as much as physical structure. Engineers anticipated how people would walk, gather, listen, and leave. Buildings became guides for movement. The success of these designs can be seen in later architecture, as stadiums and theaters centuries afterward followed similar principles. As night settles over the arena and the last spectators depart along torchlit passages, the stone structure remains silent, yet ready for the next gathering. It stands not merely as a monument, but as a solution to a complex problem: how to bring thousands of individuals together in one place safely and comfortably. And as we continue forward, we will look toward the edges of the empire and see how Roman engineers adapted their methods to different climates, from rainy northern provinces to dry southern deserts, proving that their technology was flexible as well as strong. Now we travel far from the warm Mediterranean coast to the outer provinces of the empire, because Roman engineering was not designed only for one climate. The same builders who created sunlit forums in Italy also worked in rainy northern lands, high mountains, and dry deserts. Their methods adapted to each environment, and this flexibility helps explain why their systems lasted so long. In the northern provinces, where winters were colder and rainfall frequent, roads required special care. Heavy rain could turn soil soft and unstable. Roman engineers responded by digging deeper foundations than in dry regions. Layers of stone, gravel, and sand allowed water to drain downward instead of collecting on the surface. Side ditches carried excess water away. Because of this, wagons could continue moving even after storms when ordinary paths would have become impassable. Fortified settlements in these areas also used thicker walls and enclosed courtyards to protect inhabitants from wind. Roofs were sloped more steeply so snow and rain slid off quickly. Inside, heating systems became especially important. The hypocaust floors found in bathhouses appeared even in remote forts. Soldiers stationed along cold frontiers still bathed in warm rooms because furnaces heated air beneath floors and inside walls. Maintaining familiar routines helped morale as much as comfort. Travel further east and south into dry provinces and the challenge changed completely. Instead of too much water, engineers faced too little. Here, aqueducts stretched across long distances to bring spring water to towns surrounded by arid land. Channels were sometimes covered with stone slabs to reduce evaporation under strong sun. Cisterns stored water during seasons of supply so it could be used during drought. In some desert regions, underground channels were dug to protect water from heat, guiding it gently toward settlements. Bridges also adapted. In mountain regions, rivers ran fast and deep during spring melt. Roman builders anchored bridge foundations directly into bedrock where possible. Arches were raised higher above the waterline to survive flooding. Some bridges combined stone piers with wooden upper sections so repairs could be made quickly if part of the structure was damaged by strong currents. Coastal areas brought yet another difficulty: saltwater corrosion and waves. Harbors were protected with breakwaters constructed from special concrete that hardened underwater. Engineers mixed volcanic ash into the mortar so it reacted with seawater and grew stronger over time. This allowed piers to remain stable despite constant wave movement. Ships could dock safely and unload cargo without being damaged by surf. In forested regions, wood became the primary material. Timber bridges, watchtowers, and palisade walls could be erected rapidly where stone was scarce. Although wood did not last as long as stone, the Romans compensated with regular maintenance. Replacement beams were prepared in advance, and damaged sections were repaired rather than abandoned. The emphasis was always continuity rather than perfection. Climate also affected clothing production and storage technology. In colder lands, workshops produced thicker fabrics, while warehouses were ventilated differently to prevent dampness. Grain storage buildings were raised higher above ground in wet areas and sealed more tightly in dry areas to protect from insects and heat. Every region required adjustment, yet the underlying planning remained recognizable. Communication networks stretched across all these varied environments. Relay stations stood at measured intervals along roads, so messengers could rest and change horses. Even across deserts, wells were spaced at predictable distances, turning empty land into navigable routes. A traveler crossing provinces could rely on consistent markers, finding shelter and supplies along the way. What becomes clear is that Roman engineering was not rigid. It was a set of principles: careful measurement, planned maintenance, and adaptation to local conditions. Builders observed nature first, and then designed solutions suited to it. Because they respected terrain rather than forcing uniform design everywhere, their constructions survived longer than many later attempts. As evening falls in a distant frontier settlement, warm air rises from heated floors while rain taps gently on the roof. And far away in a desert town, water flows quietly into a shaded fountain. Though the climates differ greatly, Both places share the same practical knowledge. The empire was held together not only by authority, but by shared methods of solving problems. And as we move toward the final part, we will gather these ideas together and see how Roman technology, even after the empire's political power faded, continued influencing later societies who rediscovered and rebuilt using the lessons left behind in roads, ruins, and surviving structures. As we move into the final long stretch of this journey, the most interesting part of Roman technology begins after the empire itself slowly fades. Political control weakens, armies withdraw from distant provinces, and some cities shrink in population. Yet something remarkable happens. Many of the systems continue to function for generations without the original builders. Roads remain firm beneath travelers' feet. Bridges still carry wagons across rivers, and aqueducts in certain regions continue delivering water long after the officials who ordered their construction are gone. The technology outlives the government. Travelers in later centuries often encountered these structures with quiet amazement. A person walking along a straight paved road through forests or fields might not know who built it, but he could see its usefulness. Carts preferred the old Roman routes because they were smoother and more reliable than newly formed dirt tracks. Merchants chose them naturally, and settlements grew beside them. In this way, old engineering quietly guided where people lived and traded, even when memory of its origin faded. Aqueducts demonstrated similar endurance. Some continued flowing for hundreds of years because gravity required no moving parts. As long as channels remained clear, water kept traveling from hills to towns. Local communities sometimes repaired small breaks with simpler materials, trying to preserve the precious supply. Fountains fed by ancient systems became central meeting places. Even when maintenance knowledge was incomplete, the usefulness of the design encouraged preservation. Stone bridges also survived. Because their arches distributed weight so efficiently, they endured floods that destroyed wooden crossings. Later inhabitants often built new structures beside them, yet still used the Roman foundation. In several regions, medieval builders repaired rather than replaced Roman bridges because rebuilding from the beginning would require enormous effort. The earlier solution remained the best solution available. The written knowledge survived more unevenly but not entirely lost. In monasteries and libraries, some engineering texts were copied and preserved, sometimes without full understanding of their technical meaning. Generations later, scholars studying these manuscripts rediscovered methods of proportion, surveying, and construction. Builders who examined ancient ruins alongside these writings began to realize how carefully the original work had been planned. One important lesson learned from Roman remains was the strength of concrete and arches. Later architects noticed that curved structures stood longer than flat ones, and that thick walls were not the only source of stability. Gradually, arches returned to construction in bridges and large buildings. Cathedrals and halls built centuries afterward carried echoes of Roman principles, even if their builders adapted them to new purposes. Urban planning also inherited Roman influence. Many European cities grew along the same street lines first laid out by Roman surveyors. Modern roads in some places still follow the direct paths measured by the Groma nearly 2,000 years ago. The original grid continued shaping movement long after new buildings replaced old ones. The calendar reform proved perhaps the most enduring achievement. The organized solar year introduced during Roman times remained in use across vast regions for over a millennium, guiding agriculture, religious festivals, and civic administration. Even later adjustments were small corrections rather than complete replacements. In daily life, people measured seasons according to a system first standardized in that earlier age. What makes this lasting influence gentle is that it worked quietly. Later societies did not always consciously copy Roman methods. Instead, they found existing solutions practical and continued using them. A road that already existed was easier to follow than to abandon. A bridge that still stood was safer than a new one. A calendar that matched the seasons required no replacement. Roman technology became part of ordinary life by remaining useful. If we imagine a traveler centuries after the empire's height, walking at dusk along a straight paved road, he might pass beneath an ancient arch, hear water flowing from a fountain fed by distant hills, and enter a town built around a central square, aligned long ago by surveyors. He might not know the names of the engineers, but he benefits from their patience and planning. The achievement of Roman engineering, therefore, was not simply that it created impressive structures. It created systems simple enough to function without constant supervision and strong enough to endure long change. The empire itself was temporary, but the solutions it developed, roads, measurement, water management, and organized building, became part of later civilization. As night settles over the old stones and the sound of footsteps fades along the road, the arches stand quietly against the dark sky, still holding their weight, still guiding travelers, still shaping the landscape long after their creators have passed into history. As we continue a little further, we begin to notice something very calm but very important. Roman technology was not based on sudden inventions. The Romans rarely created completely new ideas from nothing. Instead, their strength was improvement and organization. They observed methods used by earlier cultures, the Greeks, the Egyptians, and peoples of the Near East, and then carefully refined them until they worked reliably every day. Their achievement was patience rather than sudden discovery. Take concrete again as an example. Earlier societies already used simple lime mixtures, but Roman builders experimented with volcanic ash found near certain regions of Italy. They discovered that when this ash was mixed properly, the material hardened stronger than ordinary stone mortar, and even resisted seawater. They did not describe the chemical reaction scientifically, yet they recorded the proportions and followed them consistently. Builders across the empire repeated the same mixture, producing harbors, walls, and domes that lasted centuries. The same careful improvement appeared in water management. Aqueducts were not entirely new. Earlier civilizations had channels and canals, but the Romans standardized surveying and maintenance. They set inspection shafts at intervals so workers could enter the channel to clean sediment. They created distribution tanks to regulate pressure so pipes would not burst. Lead or clay pipes carried water into neighborhoods in controlled amounts. Instead of one large canal serving a single palace, they created a citywide network serving many citizens at once. Standardization also appeared in tools. Brick sizes became uniform so walls could be assembled more quickly. Tiles for roofs followed consistent shapes so damaged pieces could be replaced easily. Even military equipment followed repeated patterns, allowing armor and weapons to be repaired anywhere in the empire. This predictability reduced confusion and saved time during construction or travel. Measurement systems supported this organization. The Romans defined units of length and weight used in trade and building. A worker in one province could understand instructions written in another because the same measurements applied. When an engineer ordered a beam of a certain length, suppliers knew exactly what was required. Markets relied on standard weights, so buyers trusted transactions. Urban planning reflected similar thinking. Many towns were laid out in grid patterns with two main streets crossing at the center. This design simplified navigation and drainage. Water channels followed the street lines, and public buildings occupied predictable locations. Travelers arriving in a new city could orient themselves quickly because its arrangement resembled others they had seen before. The postal relay stations show another example of organized improvement. Instead of relying on individual riders, the Romans created a chain of horses placed at regular distances. A messenger arrived, handed the message to another rider with a fresh horse, and the journey continued immediately. The message traveled faster than any single rider could manage alone. The idea was simple, yet the systematic placement of stations made it powerful. Mining and resource extraction also benefited from planning. In certain provinces, engineers directed water through channels to wash away soil and expose mineral deposits beneath. They built drainage tunnels to remove groundwater from deep shafts. By combining water control with manual labor, they could reach resources otherwise inaccessible. Again, the idea was not a single machine, but a coordinated method. Even everyday items reveal careful thought. Oil lamps were shaped to burn steadily without spilling. Amphora jars had pointed bases so they could stand securely in sand or racks aboard ships. Roads included milestones marking distance, so travelers knew how far they had come and how far remained. Each feature solved a small practical problem. Together, they formed a system supporting millions of people. What becomes clear is that Roman technology valued reliability above novelty. A device or structure was considered successful if it worked consistently and could be repaired easily. Engineers preferred solutions that could be repeated by different workers in different places. Because of this, their methods spread widely and endured long after the original empire declined. As the evening quiet returns and lantern light glows along a paved street, the achievements surrounding the citizens seem ordinary to them. Yet beneath their daily routine lies careful planning developed through observation, testing, and repetition over generations. The Romans built not only with stone and mortar, but with habits of organization. And as we move toward the final part, we will gather together all these elements: water, roads, cities, trade, measurement, and planning, to understand why their practical approach allowed their technology to shape the world long after the empire itself had faded. As we come gently toward the end of this long walk through Roman engineering, it helps to see the empire not as a collection of buildings, but as a living system. Each piece, water, roads, trade, construction, and planning, depended on the others. None worked alone. A city needed water to support population, roads to bring food, ports to receive ships, measurements to organize building, and written knowledge to repeat methods. The Romans succeeded because they connected these parts patiently and maintained them steadily. Imagine the empire on an ordinary morning. In a distant province, farmers harvest grain and load it onto wagons. The wagons travel along paved roads to a river port. There, workers transfer the grain into ships designed to carry heavy cargo safely across open water. After days of sailing, the ships enter a protected harbor where cranes lift the sacks into storage warehouses. From the warehouses, grain moves to bakeries where mills grind flour and ovens bake bread. That bread feeds citizens who work as craftsmen, officials, and soldiers. who in turn maintain the roads, aqueducts, and buildings. The entire cycle repeats quietly without dramatic attention. Technology here is not a single invention, but a chain of organized activity. Maintenance played the central role in keeping this system alive. Inspectors walked aqueduct lines searching for cracks or blockages. Road crews replaced worn paving stones. Harbor workers repaired ropes and docks. Public caretakers cleaned bathhouses and fountains. These were ordinary jobs repeated daily, yet they prevented collapse. The Romans understood that building was only the beginning. Preservation mattered equally. Because of this continuous care, their structures aged slowly. A bridge did not wait for complete failure before repair. Small adjustments were made early. Channels were cleaned before water stopped. The system depended on attention rather than emergency. This attitude explains why many remains lasted so long. The builders expected future generations to use what they created, and they prepared for that future by making repair possible. We can also see how technology shaped behavior. Citizens trusted public fountains and gathered around them. Merchants relied on predictable roads and scheduled deliveries. Officials organized meetings according to shared calendars. Daily life adapted to the steady rhythm provided by engineering. People planned journeys knowing where milestones stood and where stations offered rest. Even entertainment depended on predictable structures where crowds could gather safely. After the empire weakened, many communities continued following these patterns even when they no longer knew who had designed them. A town remained near a road because travel remained easier there. A marketplace stayed beside a fountain because water drew people together. Knowledge faded gradually, yet practical usefulness preserved the structures. The lasting influence of Roman technology therefore lies not only in ruins still standing, but in habits that continued unconsciously. Later builders, seeing arches still holding bridges, copied the shape. Farmers using the calendar planted at the same seasonal times. Travelers following straight routes preferred them to winding paths. Over centuries, the original intention blended into everyday life. If we imagine evening settling once more over the ancient city, fountains continue to flow as shadows lengthen. A cart rolls across a stone street. In the distance, an arch frames the sky. The people moving beneath it think only of their daily tasks, not of the surveying, measuring, mixing, and planning that made their world stable. Yet all around them, the quiet work of Roman engineers continues to guide movement, provide water, and support comfort. And with that gentle picture, we can rest our thoughts on the understanding that the Romans did not change history through a single dramatic discovery. They changed it by organizing knowledge into reliable systems, repeating them patiently, and maintaining them carefully. Long after emperors and armies passed into memory, the practical solutions they built remained part of ordinary life. We arrive now at the quiet end of our long journey, and instead of looking at a single building, we look at a landscape. Hills, rivers, towns, and coastlines, and across them, faint but still visible, the careful lines left by Roman hands. A straight road cutting through countryside, a worn milestone beside a path, a stone bridge still carrying footsteps, and sometimes a broken aqueduct arch standing against the evening sky. None of these alone explains the Roman achievement. Together they do. The Romans did not leave behind only monuments. They left behind a way of thinking. When they faced a problem, too many people needing water, too much distance between cities, too much rain or too little. They did not search for a single heroic solution. They observed patiently, measured carefully, and then created systems that worked every day. Their goal was reliability. A fountain must flow tomorrow, just as it did today. A road must remain usable after storms. A calendar must still match the seasons next year. Because they thought this way, their work blended into daily life so naturally that most citizens barely noticed it. Generations lived surrounded by these systems. Children grew up hearing water run from fountains and assumed it had always done so. Travelers followed roads without knowing someone had once measured every slope by hand. Merchants trusted bridges that had stood longer than their grandfathers could remember. The technology became invisible because it was dependable. And perhaps that is the greatest success any engineering can achieve. To be so reliable that people forget it was once an invention. Centuries later, long after imperial authority disappeared, people continued to build beside those same roads and draw water from the same channels. Even when ruins appeared, they were not useless ruins. They became guides. Later builders studied the arches and learned balance. Farmers followed the calendar and planted at the right season. Towns grew where the old roots met. The empire as a political power faded, but the practical world it created continued quietly underneath new societies. If we imagine one final evening in the ancient city, the sun lowers beyond tiled rooftops. The last carts roll over stone pavement. A fountain still pours into its basin. Somewhere far beyond the hills, water travels gently through a channel laid with careful slope 2,000 years ago. No noise announces its journey. It simply continues, steady and patient, just as the engineers intended. And so the Roman legacy is not only in what they built, but in how long it kept working. Roads guided footsteps, arches held their weight, and organized knowledge passed silently from age to age. Their technology did not shout through history. It endured through usefulness. If you enjoyed this slow walk through the ancient world, take a moment to like the video, subscribe to the channel, and share which part of history you would like to visit next. There is always another city, another century, and another quiet story waiting for us to explore together. Good night and rest well, until our next journey into the past.